So today we'll be looking at downsampling. Okay. So in the previous lectures last week, what we looked at was the effect of aliasing in your picture. Okay. So all that is still similar to what you've seen in 1D, and but we looked only at the effect of having a continuous signal, and if you sample the signal, what the effect of that, and you can have aliasing. But in a way, it's not that interesting to us because there's nothing you can do. Okay, so when you take a picture, if the frequency in the real world is higher than the spacing of your the spatial frequency of your pixels of your sensors, then there's nothing you can do about that, right? So here we're going to look at something that has a direct impact on what you're doing, which is downsampling. So in this case, what you have as a starting point is your discrete signal, so the picture, so we call it F here, and we want to generate a downsampled version of that signal, and basically what we have is a rate n, so we say we're only going to save every second or third or fourth or whatever number of integer you have of pixels in the original picture. So most of the discussions here will be using 1D diagrams, but basically you have the same equivalent in 2D. So on the left here you have your original, in the blue line is your original continuous signal, and what you've done is you've sampled that, so that would be the pixel sensors on your camera. Right? And what we want to produce is this more sparser version, so the red dots here you have on the right. So here we have a downsample factor of 2, and in most of the examples we use that number. Right, so here's the gist of the problem, okay? So actually I'm going to switch directly to this version here. So basically you have your signal, okay? And okay, so this is your spectrum. The spectrum you're looking at, and you have a sampling frequency which is at 2 pi over d. Okay, so in this example, d is the space between your samples, and we're going to say that's the same. So we have dx equal dy is d is the same. Okay, so we just simplify everything. Okay, so that's your sampling frequency, and what you obtain is so you have your spectrum, and your spectrum will go about like that, symmetric around 0, and sorry. Okay, so basically you have your signal that gets replicated at multiples of this fundamental sampling frequency. Okay, so that's what you get. Okay, so that's your sampled image. When you look at the Fourier spectrum of that sampled image, this is what you get. And you get this replication because of the sampling of the continuous spectrum. All right, so that makes sense? So we're looking here at the Fourier transform of the sampled image, okay? Okay, so this is omega, and your f, so you had your f of mn, okay? So when you look at the Fourier transform, this is what you get, okay? Obviously, when you will downsample, as you know, you're going to produce more of these guys, and basically what will happen is you're going to have an issue is that your sampling frequency, say if you downsample by 2, your sampling frequency will go from 2 pi over d to pi over d, okay? So basically you're going to have, instead of having the replication every 2 pi over d, now we're going to have a replication every pi over d, which is a bit of a problem because what you have is, so your original signal looks like this, but now this signal is going to be replicated here as well. Okay, so basically here, this is the summation of these two signals, and really what you get is this part here, okay, where you have aliasing, will add up to each other. So really what you get is something like looks like this. So you have pi over d, 2 pi over d, minus pi over d, and minus 2 pi over d. And so you get your parts here. They get something like that. Okay, so basically this is just the combination of the two. So when you add the two, really what you get is this kind of higher level. Okay, so if you want, you will get something like that. Okay, so the final outcome of your signal. Sorry, I'm missing something here. That should have gone here. All right. Aha. Right, so sorry about that. So the final version, what you get is something like that, okay? So you have a peak at every pi over d, okay? So the new sampling frequency is pi over d, so it repeats every pi over d. But the signal, because now the alias part gets added up, you don't have this dip now in the frequency. The frequency is almost flat here in this case, okay? Does it make sense? All right? So you go from something that looks like this in the frequency domain to something that looks like this, okay? So that's the effect of downsampling. So downsampling alone is not good, okay? So what you have to do is to apply some kind of filtering operation that will allow you to do this downsampling and still try to preserve as much as you can from the signal and avoid the aliasing. And so what we're going to do is we know that the issue here is this aliasing part. So what we have to be careful of is to say, right, so when we start from, so I'm going to redraw this guy again, okay? Well, maybe just skip that. All right, so we say this is the frequency we get, spectrum we get from the sampled image, digital image. Somehow what we need to do is, okay, so we know that we're going to be sampling at pi over d now. So we know from Nyquist that we should remove all this part here. Okay, so we should be very careful of what's going on. We can only really keep that part of the signal. So somehow we need to cut off the frequency here and only keep these lobes here. Okay. So somehow we want to devise a filter that will put these guys to 0, okay? So when we apply then the subsampling, what will happen is that when we do the replication, the aliasing will be gone, okay? So if we had done that, if we had cut off these frequencies, then the aliasing in these parts wouldn't exist, okay? That wouldn't be an issue. All right, so I do that again. So if we go from here, then I'm trying to make space. Then we apply sampling, or subsampling, I should say. So when you subsample, what you'll get is so 0. And so you have this part of the signal, but the replication here will come here, and so will just be tiled nicely. Okay, so you don't have any crossover. The frequencies are nicely spread now. Okay, so the vertical bar here is just to say that's where you cut and spliced the frequencies. Okay, and because we nicely cut off the frequency between the range pi over 2D and 3 pi over 2D, then we made sure here that there will be no overlap here. Okay, so when this guy is going to move towards here, that's not going to be a problem. All right, so you have no issue. So that's kind of what we want to do. Okay, we want to find a filter that will go from here to here. We're going to apply that to our picture, and somehow by doing that, then we apply the subsampling, they'll all be fine. All right. So this is our goal, trying to find the optimal filter to apply on the picture before we subsample. Make sense? So I'll say that again because it has to be super clear. If you just subsample your picture, you will cause aliasing. You will see all the artifacts we've seen last time. Okay, and so we'll see these ghost frequencies. We'll see all these issues due to the aliasing. And the aliasing, we know this is caused by that. So when you subsample, you're going to replicate these lobes at a higher rate, and basically they're going to overlap, and the overlap is going to create this totally different spectrum you had before. Okay, so the idea here is we're going to say, right, so we're going to take the original picture, we're going to apply a filter, and the filter will have the effect of cutting off these frequencies that might cause aliasing, and if we kill off these frequencies, then when we do the subsampling, we'll end up with something which is just right, okay, where there's no aliasing. Okay, so that's a principle in 1D. And basically, the filter step will go in two parts, okay? So the first thing we're going to do is trying to go, well, there's different ways of doing that, but I think the simplest way is to go into two parts. So the first part is try to recover the original Fourier spectrum, okay? So what I had here, in fact, was the sampled Fourier spectrum, okay? And I want to just try to recover what the original Fourier spectrum was. And so if I have the original Fourier spectrum, then I can actually, will be easy to just do a one cutoff, okay? All right, so let's try to do that, okay? So we have, all right, so we have this spectrum here. So how would you go about trying to recover it's a question for you now, okay? So if we have this, signal, how would you what kind of filter would you apply to get back the original spectrum of the analog signal? Okay, so this is the spectrum of the digital signal. How would you go about trying to find, where is the part that corresponds to? What would the original spectrum look like? Just the middle one, right? So what we want to apply is some kind of ideal pass filter on that. So we just want to say, right, I have this filter, okay, which has all this replication, but somehow what we want to do is to multiply that by some kind of rectangular shape, and this guy is going to be between minus pi over d and here be pi over d, and be something like that, okay? So you say if you multiply this sampled version by this guy, then what you get is only this version, okay? Between so pi over d and minus pi over d. All right, so we've seen that, okay, so that's the rectangular function, and there's one thing we need to do again, okay, because remember, like, sampling has two effects, okay? So has the effect of replicating the spectrum, but as well has the effect of scaling it down, okay? So somehow we need as well to apply to rescale the factor to kind of bump up to the level we were at before, okay? So typically, we need to multiply, so that would be something like f of, the exact formula would be something like multiplied by d squared, so if in 2D, okay, so if in 2D it would be d squared times rectangle of omega, all right, I want to be sure here. All right, so this is what you get. Right, so basically the formula, exact formula for that, you look into the slides, but basically you have the d squared, the d is your sampling the distance, and to get back to what you best estimate for the original spectrum, you need to apply this filter. So d squared is for rectifying the amplitude of your Fourier, and this guy here is just to cut off any kind of higher frequencies. All right, so that's the first part of your filter, okay? That's what we're going to apply. And then after, we can apply the, all right, so we try to recover the original signal. So that's the first part. So once you have the original signal now, what we need to do is to apply a proper, what we need to do now is to subsample, okay? And we will need to take care of the subsampling rate, okay? So if we want to have now a sampling frequency, so if we say now the subsampling frequency is n omega s, so omega s is the original sampling frequency, okay? So that's 2 pi over d, okay, the original sampling frequency. Now we say, well, we're going to have this new frequency. And so, sorry, there should be that, all right? So what we need to do now is to have a new cutoff filter that will go to wherever we want to go, okay? So we need to have, we say, okay, so we have f of omega times this new version, okay, which would be basically at pi, so 2 pi over n times d, and minus 2 pi over nd, okay? All right, so it's kind of the same trick here, okay? And we say, well, we recovered the original spectrum, but we know there is too much because we're going to cause aliasing, so we need to cut off the frequency at the new sampling frequency. And we know how to do that. We know that this filter again. All right, so basically, so I'll just make sure I haven't made any mistake here. The new frequency for this filter would be then, so the original frequency we had times this vector, this filter, which is the ideal low-pass filter, which is simply removing the bad frequencies. All right, so that's the final version of, I don't know how to call that, but okay, so that says, okay, the frequency after all we've done should look like that, okay? So the filter we need to apply is this part, okay? So the combination of this filter, if you want, that will kind of recover the original one, and this filter, which is going to be ideal low-pass filter to make sure we are at the correct sampling frequency. All right, so just combine this. Yes?
The first rectangular, is that not, like, does that actually need to be there? Wouldn't the second one take care of that as well?
Well, exactly. So, good point. So that's going to say now. that this one, obviously, the cutoff point is lower, okay? So this one, this rect times this rect actually is just equivalent to this rect here, okay? So the exact formula now, like you can delete this part because this part is unnecessary, so it's just d squared times rect of that, okay? It looks a bit messy on the slides here, but on the actual slides, it'll just be fine. Okay, so this is what we say here. So we will combine the two effects. You end up with, you can remove that part because that part is, the pulse is shorter than this pulse, and therefore your final formula is something like that. Okay. Okay, so what we've done here is if we design the ideal filter to apply in your to your picture, so it solves all your problem. Okay, so when you do that, basically what you've done is you cut off all the aliasing problem. When you do, you can do the maths. Okay, you can realize actually the filter is separable. You got sinc functions again as usual. It's all looking good. But again, this is in the continuous domain, so you need to sample that. Okay. And so when you have when you take the correct sampling values, this is the discrete version of that. Okay, this is the formula you get. Okay, so I separated the two coordinates into two colors. So you have blue and green. Green is not necessarily very visible here, but basically you get a sinc function. And what is interesting, okay, is that the elements only depends on the resampling or the subsampling factor n. Okay, so if there's no mention of the original base frequency or original sampling frequency or anything like that. So we don't need to actually really come back to the original picture. We don't need to know what the original frequency was for the sampling. We only need to know what the change of the frequency is. So if we subsample by 2, then this curly n here is 2, and then you can design your impulse response for the filter in that case. Does it make sense? Okay, so we end up with a signal which is sinc function, and compared to 1D, the only difference is we have now a sinc in both x and y direction. And importantly, this filter doesn't depend on the original frequency, but only on this factor of how much we're going to reduce the size of the picture. So we have, where is this? Do we have that somewhere? Right, so remember the sinc function, okay? So we looked at the sinc function, and we know it kind of ripples, basically, along the way. The problem you have is the ripples, okay, you have in the sinc function are of infinite, like the spread of the filter is infinite, okay? And you cannot do that in any practical way, so you have to stop at some point, okay? You have to say, I'm using 15 plus or minus 15 pixels to apply my filter because, you know, I don't want to use 1 million pixels, okay? And the problem with that, of course, if you stop straight away, this is the kind of effect you have, okay? So if you apply, so you have a pulse function here, and we apply the sinc on the pulse, okay? And this is what you see on the left, the effect of applying this sinc filter on the pulse function. And you can see if you just stop wherever you can in the accuracy, you get all this ripples effect, okay? So it's quite noisy here, and you know, it keeps on rippling, and the response, basically you have this these rings of, you know, dark and bright and dark and bright, like a bit like waves, okay? And that is because you had to stop, you had to truncate the filter to some extent. So what people do usually is you apply beforehand, you don't apply the actual sinc filter, you apply a sinc combined with some kind of windowing function. So this is an example of windowing function, okay? So this is Forgot which one it is. But so if you apply this windowing function, basically you're going to say, well, all right, I'll just show that very quickly. So you say my sync function look like that, and that's not very useful because it goes to infinity here. But what you can do is you can apply a global void function, and you're going to multiply both signals, and what you get at the end is more something like that. And then after here it's 0, here it's the values are 0, and you can truncate. Okay, so you have not something going to infinity, and you have a nice, more well-behaved function. All right, so, and this is when you've done this effort, okay, so here if you use a Hamming window, you get a much smoother response, and it's a bit better, okay. So in MATLAB, this is how you do it, okay, so you set so let's do that actually, let's run that. Okay, so let's say the subsampling is 2. We're going to say we're going to look at a signal going from -16 to 16. We're going to use the normalized sync function. All right, that's your signal that you get. And what we're going to do is we're going to apply a windowing function. In this case, the Hamming function. And if you want to see what the Hamming function looks like, it's something like that. So the middle sample is 0, it's 1, okay, so the gain is 1, and then after it tails off, and basically you want to cut off the values at the extremities. Okay, and so the combine effect is just do a multiplication. So in MATLAB, dot multiply means I multiply element by element. And so this is what you get. So if you compare both, okay, so you can see the ripples in the original version are much stronger, and they take them a much longer time to kind of tail off, whereas in the windowed version it tails off much quicker, and basically after we guarantee that after my 15 pixels either side, then the response is actually 0. Okay. So if you want to apply something in 2D, this is what you do. Okay, so just a matrix multiplication. So H transpose is your vertical version. H is just your horizontal version. So if I do H transpose by H as a simple matrix multiplication, it does the pointwise multiplication, and what you get in this case, how do you get that? It's mesh, I think. You get this version, okay? So you get the ripples going high up here, and then both in the X and Y direction. But importantly, in this version, it tails off, so it's bounded, so plus or minus 15 pixels, and you're good to go. All right. So, right. So this is kind of a bit complicated. The reason why I spend a bit more time on that is because usually this is an exam question. Okay. So this whole part of understanding, not necessarily in detail on how the do you get the Fourier transform and all this kind of stuff? It's because to understand the effect of frequency on, of downsampling on the frequency, on the aliasing, I'm trying to see what needs to be done, what kind of ideal filter you need to apply to cut off these frequencies and to rectify for the loss in the amplitude and so on. So all these little aspects needs to be understood, and so just look at that in detail and be aware of small detail tricks like the sampling and so on. So is that actually used in real life, okay? I mean, do actually people use a sinc function? The answer is, hang on a second, I'll again change the light. All right, so the question is, does it have an effect, okay? And you can see the answer is yes, because this is the original version on the left. If you subsample by 2, okay, and to see the effect again, look at the edges. They all kind of look jagged a bit, okay? It's probably better for you to look at the actual slides, but basically yeah, every time you have an edge that comes at a diagonal, yes?
What's the difference between the two omegas, one uppercase, one lowercase?
Sorry?
There's the omega that looks like a double E, and then there's the omega that looks like a
Right, so the small omega, so the omega looks like a, all right, so the question is what the difference between this omega and this omega, okay? So I usually use this omega for the constants one, okay? So omega here would be just if you have a function of the frequencies. That's just the angular frequency you're looking at. And the omega here, I use it, for instance, for the sampling frequency. So that would be omega s. Or if you have a fundamental frequency, I'll use omega 0 as well. Okay? So just to say it's a constant. Okay? So it's big omega if you want. All right? Okay, so this is the version, and so original and all right, so sorry again. This is the non-aliased, okay, and this is the anti-aliased, okay. So all right, so here's without aliasing. So without anti-aliasing, okay? So we didn't apply, we just applied this subsampling straight. You can see the jagged edges, the texture becomes a bit strange here. It looks a bit noisier somehow. And with anti-aliasing, the picture is a bit smoothed out. There's less visible artifacts coming into the picture. You might naively think that this is sharper picture, the non-anti-aliased version, but you have so many, so it's true it looks a bit sharper. That's because you kind of boost you have more high frequencies. So your eye is tricked into thinking this is kind of sharper, but that's because actually you put more high frequencies because of the aliasing, okay? So when you apply this sinc filter, then you preserve the amount of the frequencies you have, and you get a better filter. All right, so the sinc filter is quite hard to implement correctly and to get good results, and usually you need quite a lot of taps. So remember, taps is the size of your filter, okay? So if you have, if you use 16 or 16 taps, means you use 16 pixels, okay? So in this example here, to get something reasonable, we had to use 33 taps. So 33 pixels to be able to take decisions. And that's quite big, okay? So usually what we found to be more reasonable is to just use a Gaussian filter, okay? So you've seen that in the previous lab. Gaussian filter is just defined by this simple equation here. And basically, it's a low-pass filter, but without the fanciness of the of the sync filter. And so it's not as ideal, it's not as, you don't pack the frequencies as nicely, but the visual effect is not much difference, okay? So really in practice, I'd say what you do is you just keep in mind that when you downsample the picture, you probably should blur the picture to some extent, okay? And Gaussian filter is acceptable, sync filter is ideal, okay? So if you use a sync filter, it's the best filter you can use, but the blur probably will do the job okay. The other thing, which is upsampling, okay? So here we looked only at downsampling. So there's another problem, which is upsampling. So you have a picture, you're trying to make it bigger. And obviously that's a much harder problem, okay? Well, it's different difficulty, okay? So if you have a large picture, you want to downsample it to something, if the ratio of downsampling is say 2 or 4, if you want to downsample by 4, it's okay, the picture will look nice. If you want to upsample, it's much harder to get good results because basically you need to invent details, okay? So you have a small picture, now you want to have bigger pictures that look still sharp, okay? So basically you bought an old DVD and the resolution is quite poor, you want to play it on a 4K TV, you know, you need to upsample it, okay? So TVs nowadays have lots of hardware to do that, to try to upsample and create details where you didn't have details and keep all the edges sharp and so on, but it's quite hard. That said, the downsampling, okay, so we've seen the sync filter, that kind of breaks down to a point, okay? So if you look at, say, icons you have on your computer, you go from a very big picture, say the logo of the company, to a very small picture. And when you do this, okay, when you apply these filters, you're going to lose a lot of vital information. And usually people, when they look at thumbnails or icons for pictures, they almost have to go manual to kind of still represent in a different way, in a very small scale, what the picture looks like. So actually this is quite a very hard problem to go down at very low level, very small pictures. And there's quite a lot of research on that particular problem. All right, so this is it for downsampling. So so tomorrow we're going to start looking at the hard transform. I don't know if I put these slides up. I'm going to put them today if I didn't. And basically we're going to start again with a refresher on Huffman and coding and all this kind of information theory stuff. So that will be tomorrow. And on Monday, we're going to start the hard transform itself. And on Tuesday, we're going to start the lab. So there'll be a 2 weeks lab again. And we're going to finish the hard during the week after that. Okay?